Physics 2120. And we're going to do an example problem, one that will resemble some of your homework problems. Now, we're going to be working with electric fields. And so let's review. Remember that force between two charges is the constant K times Q1 times Q2 divided by the square of the radius between them, divided by r squared. For an electric field, the electric field is created by one charge. And so the electric field created by charge 1 is KQ1 over r squared. It's the force equation with one of the charges taken out. And the force on charge 2 is going to be the charge 2 times the electric field created by charge 1. So this would be the electric field from charge 1 times charge 2. And this is very similar to what you did with Newtonian gravitation. You remember the force of gravity was equal to mass times g, where g is a gravitational field. The same thing applies here, except the electric force is instead of mass times gravitational field, it's charge times electric field. Okay, now our problem is this. We have the x-axis laid out, and we have two charges on the x-axis. Charge 1 is 5 nanocoulombs, charge 2 is 25 nanocoulombs. And on the x-axis, charge 1 is located at the 30 centimeter mark, and charge 2 is located at the 60 centimeter mark. And we're wondering where on the x-axis, where on this meter stick we happen to be working on, is the electric field going to equal 0? Because if you think about it, the electric field from charge 1 is going to be here. Here's going to be the electric field from charge 1. We'll call that E1. And the electric field from charge 2 is going to be pointing the other direction. These are both positive charges. So this is E2. And where the electric field equals 0 is where these charges add up to be 0. And that happens when the electric field 1 is the same magnitude as electric field 2. Once you understand that, you also have to take note of one other thing. Radius 1 plus radius 2 starts at 30 and ends at 60. So radius 1 plus radius 2 is 30 centimeters, or 0.3 meters. Now, since electric field is electric field 1 is KQ1 over R1 squared, and electric field 2 is KQ2 over R2 squared, then all we have to do is look at our equation and say, what cancels out? Well, you can see that if it's on both sides, it's going to cancel out. The radiuses are different. They don't cancel out. The charges are different. Q1, Q2, they're not going to cancel out. But this constant goes away. Now let's put some numbers in here and see what we get. All right, Q1 was 5 nanocoulombs. And it's over radius 1. I don't know what radius 1 is yet, so I'm just going to put it in as R1. But it also has to be squared. Again, always start with a formula or you'll forget, like I almost did. Charge 2 is 25 nanocoulombs, and here's radius 2 squared. Now, do you notice something else that's going to cancel out? Remember, units are just like numbers. They follow the same rules. So we can actually get rid of our nanocoulombs here. Now we're going to do a little math trick. And it comes out of cross multiplication. What we're going to do is we're going to take this value and this value and switch them. And what we end up with is R2 squared over R1 squared is equal to 25 over 5. Now, since both of these are squared, we can rewrite this And I'm going to go back over here. Let's make a little arrow to show where I'm going. I'm going to do another line here. But what I'm going to do is I'm going to take R1 over R2. So R1 over, R2 over R1 squared equals 25 over 5, which is 5. So good so far. Now, what do you want to do to get rid of something squared? Well, you take a square root. And so if we take the square root of both sides, we get this. We get R2 over R1 is equal to the square root of 5. We'll just leave that be for now. Now, R2 over R1. Now it's time to bring in that thing that we reminded ourselves. R1 plus R2 is 30 centimeters. So R2 is equal to 0.3 meters minus, and all I'm doing is dragging this over here, minus R1. Now, this is a math trick, but it's a good one. Because now what I'm going to do is I'm going to rewrite this. I'm going to say this is 0.3 meters minus R1 over R1 equals the square root of 5. Now if you recall, this means that we can split this up. And splitting it up, okay, one more time. Splitting it up gives us this. 0.3 meters over R1, 0.3 meters over R1 minus R1 over R1. And R1 over R1 is just 1. And that equals the square root of 5. Okay? Now what? You take the negative 1 over to this side, and we have 0.3 meters divided by R1 is equal to 1 plus the square root of 5. Now the square root of 5, as I recall, is 2.23. Thank you. So this is 1 plus 2.23, which is 3.23. Okay, now I'm gonna roll up here just so we can finish this problem. And I'm starting with this right here, 0.3 meters divided by R1 equals 3.23. Now, this may look complicated, but it's really not. Because if you remember your basic math, you will remember that if I have simple numbers, for instance, if I have 6 divided by 3 equals 2, and I have 6 divided by 2 equals 3. Oftentimes students get confused on this, but if they remember these simple numbers, you'll remember that the 2 and the 3 get to switch places. And it doesn't matter what the squiggly lines look like, the math is the same. Look what gets to switch places down here. These guys. So 0.3 meters divided by 3.23 equals R1. And now it's time to reach for the calculator. And we have 0.3 divided by 3.23, and we get 0.092 meters. All right, 0.093. All right, so 0.093 meters, or 9.3 centimeters. This is R1. Now, it's important to note that this is not where the electric field is 0. The electric field is 0 9.3 centimeters over from here. So 30 centimeters plus 9.3 gives us our point. And it's 39.3 centimeters. This is our answer. This is where, on the x-axis, the electric field equals 0. If you had solved for R2, and you could have, then you would have had to subtract your answer from 60 centimeters to get there. And finally, look at it and see if it makes sense. This is a big charge compared to this small charge. And so the electric field is going to be strong versus weak, which means we've got to get fairly far away from that electric field before its magnitude is equal to the magnitude created by this one. And that meets our expectations. It's what we expect.